Thank you. Yeah, my name is Wesley Chambers, and together with my colleagues at NASA and Johns Hopkins University, we've been working to analyze some data from a Plume-Surface interaction test that was conducted last summer. So I'm going to be talking to you all about that today. Now, Plume-Surface interactions occur whenever you, or can occur whenever you have a propulsive launch or landing. On Earth, we use landing pads to mitigate that. But for something like an unimproved planetary surface like the moon or Mars, gas plumes can cause interaction. So, stuff gets blown around, debris which can damage either your spacecraft or surrounding assets. So I'm working on, whoops, that was not supposed to show up right away. There we go. Yeah, so NASA's Plume-Surface Interaction Project is a collection of activities that is meant to mature testing, modeling, and instrumentation capabilities to understand Plume-Surface interaction phenomena. So we have a suite of activities going on, and today I'm going to be talking to you specifically about our physics-focused ground test. Whoops, that test was supposed to move out of the way, it didn't, but we're talking to you about our physics-focused ground test, and specifically the test 1, which occurred last summer. And so I'll be looking at that here. So this test occurred at Marshall Space Flight Center in our 15-foot vacuum chamber. So there's a picture of the setup here on the left, diagrammed on the right. And this was a Plume-Surface interaction test that was conducted with a supersonic nozzle, heated inert nitrogen gas. We had basically a half-space soil bin here that was instrumented with 3 high-speed cameras so that you could see with this kind of cutaway view, a view of the PSI phenomenon as they occurred. So in a little more detail, here's kind of a diagram. This is our nozzle plenum and the nozzle right there. You see basically the flow gets bisected by this splitter plate, and then you end up with granular material getting blown around. On the right side here, this shows approximate fields of view for our cameras. So we had a cratering view camera, and then a couple of high-speed cameras also to get ejecta. And these were placed basically to try to intercept the ejecta as it flew out from the interaction on center. Now, the time resolution was chosen. Crater depth evolution happens more slowly than the particles that are flying out. So this was a 5,000 frame per second camera, and these were 25,000 and 775,000 frame per second for our ejecta cameras. So this is just to give you an idea of what it looks like. This was kind of an atypical crater camera view, but just to give you an idea of what happened kind of at the very beginning of the experiment as the nozzle turned on and you begin to see ejecta flying out. This was conducted with BP1, lunar soil simulant. The parameters are listed there. The H/D, that's our nozzle height normalized by the nozzle diameter of about 2.5 centimeters. The mass flow rate, and the ambient vacuum. So the vacuum chamber pressure was varied from Mars ambient down to the lowest facility pressure, which was about 20 millitorr. And then we had nozzle heights ranging from 3 to 13, height or nozzle normalized by the nozzle diameter, and then 2 main mass flow rates that we use. It varied from 0.32 to 8.6 grams per second. We used a range of simulants. Our main ones were monodispersed silica sand and BP1 lunar soil simulant, but we also used a few basically mixtures of those and glass spheres as well, so we kind of had a simple simulant. The idea was to look at how this varies over a range of different simulant types. So for the past year or so, along with my colleagues at Johns Hopkins, we've been working to analyze this data. So on the left, you can see this is the algorithm I've been working on to recover crater profiles in time. And on the right, one of my colleagues at Johns Hopkins has been looking at ejecta particle tracking. And we're doing this to really try to understand, okay, what happens during these PSI events, and how do the particles move? What does the crater morphology look like? So moving forward here, to give you kind of a preliminary view of what we've been doing, I'm going to focus on the part I've been working on, which is crater profile analysis. And the depth versus time, depth on the y-axis, time on the x-axis, is kind of a good sanity check of the algorithm, and also it's a parameter of interest. So I'm going to take this plot, I'm going to switch it to a log-log plot. And then, since this is kind of preliminary and not like fully rigorously calibrated yet, I'm going to look at the monodispersed silica sand data here, just pull that out, and then put this over in the corner and show you some comparisons. So in these three comparisons I'm going to make real quick, you'll notice that the depth versus time is shown over here. Those correspond to these two cases, and this top case is going to stay the same in these three comparisons. So this shows a difference in vacuum pressure and how that affects Plume-Surface interaction. So this is Mars atmosphere, and this is our lowest vacuum pressure, which is meant to simulate kind of lunar conditions. You can see that the plume expands more before it hits the surface, and so you end up with this kind of annular cratering versus more on-center cratering in like a Mars-like atmosphere. Show difference in mass flow rate, as you might expect. Now these are both at kind of our hopefully lunar relevant lowest facility pressure, where you see more annular cratering. You can see that obviously as you ramp up your mass flow rate, then as you might expect, you see an increase in amount of material ejected. And then the last comparison I want to show real quick is difference in nozzle height. So what's interesting about this is the same case once again, where we see that annular cratering. This was at our H/D of 10. Same parameters, except now we lower this down to an H/D of 3. And that annular cratering behavior is gone, and we see kind of a broad, relatively shallow crater at this lowest facility pressure. So in conclusion, we've conducted, it's called Physics-Focused Ground Test 1. It's a small-scale inert gas supersonic Plume-Surface interaction experiment. Bit of a mouthful, but we see significant variation in parameters or in behaviors across the parameter space as we vary our nozzle height, our ambient pressure, and as in addition, I didn't show it here, but as you vary the simulant, we also see some changes in behavior there. So the qualitative kind of things that I showed you here, it allows kind of a judgment about mitigation strategies, but we're doing ongoing analysis to do these crater profile measurements, track ejected particles, understand these behaviors with the goal of being able to reduce risk to landers, robotic and crewed. And these analysis products will be used by other members of our project to do things like model validation. And so with that, if there's any time, I'll take questions.